Okay, thanks for coming this morning. My name's Bloice. I'm a Wireshark core developer, and what we're going to talk about this morning is Wireshark Dissectors. And there's three reasonable ways to go about that currently in Wireshark. So a little bit of audience participation before we start. Has anybody been to this talk before? I have run it previously. If you have been before, I'm afraid you'll be a little bit disappointed because it's exactly the same as it was last time. Also, has anybody tried to do dissectors before? Have you actually had a go? Oh, a few there. Succeeded? Not really. Okay. Hopefully this will give a little guide. This is very much a bird's eye view because there's a lot to do in a dissector, and in the time available I can only really cover it sort of briefly, but hopefully it gives you a view onto what we do with dissectors. So myself, I'm a software developer with Trihedral UK in Aberdeen in Scotland. We produce a SCADA toolkit which is used in industrial control systems, and my use of Wireshark there is with the industrial telecontrol protocols used in SCADA systems, Modbus, DMP3, Allen Bradley, Rockwell, all these industrial control protocols that move from their serial days now move over to TCP/IP, UDP and other things like that. So that's where I use Wireshark on the day job. And I first contributed to Wireshark 1999, can't believe that's 16 years ago. I work on the DMP3 dissector, and I'm a frequent contributor on the Ask Wireshark website, mostly fixing people's comments and formatting to make it look nice and solve my OCD issues. So what we're going to talk about today is a brief overview of Wireshark Internals, about the Wireshark application as a whole, and where dissectors fit into that. Having awareness of the framework the whole application gives you helps a little bit, I think, in writing a dissector. And then in dissectors themselves, a brief overview of what they do, some three ways to implement dissectors currently, and a little discussion on the complexity of doing so in each of the ways and performance trade-offs. So Wireshark itself, the application, it's basically a large framework. From the dissector's point of view, it's a large framework for loading or making captures of the network traffic, then dissecting that, and then allowing the visualization of that dissection for users to interpret the capture that they have. And the framework within Wireshark abstracts away the whole issues of the capture files or obtaining the data from dissectors with live wiretap. That reads all the different capture file formats, and that also runs live captures via live PCAP or WinPCAP on Windows. And the framework also provides lots of utility functions for dissectors to call when dissecting data. So the framework you can view is actually a huge API. Unfortunately, it is quite large, and there's lots in there that allows you to, within the dissector, make the sufficient calls that you need to cause a dissection to come up in the visual tree. And that's the last bullet point there. The framework then takes the dissector output and causes that to be displayed in the packet list and the packet tree. So dissector overview. A dissector is interested in only a particular part of a capture. You have the usual network layering model, so from Ethernet to IP to TCP. Those are all inbuilt in the product, so you won't really be writing a TCP dissector. But then application layer dissectors is generally where people are involved above that. So they'll be writing something that's hooking in, as it were, to another layer already in the system. So dissectors then have to register their interest in that data. So you have to register with the lower level protocol, e.g. for instance there, TCP port 54321. I've invented a protocol that we're going to use today that runs on TCP port 54321. Lots of protocols have IANA assigned ports, so that's a fairly easy registration. Other protocols, unfortunately, are much more dynamic in their port use, so you might have to use what's called a heuristic dissector. Heuristic dissector registers, say, the TCP and says, well, anything you don't know about, let me have a shot at, and I'll have a look at it and determine if it's stuff I want to handle. And then all the heuristic dissectors get called and each get a chance until one of them says, I can handle that data. So whatever way the TCP dissector, for instance, decides, okay, we've got a dissector that can handle this data, it will hand off the payload body. You'll get a buffer of data that's the payload body with all the TCP, IP, Ethernet stuff stripped off. You just get the data body. And a dissector then has to pick apart those bytes in the body depending on what the actual elements of the protocol message mean. And each element of that protocol message may have a type. It might be an integer field, a string, or a bit field, a timestamp, and lots of variations. And within the Wireshark framework, we have a lot of element types that you can declare or call to indicate this part of the payload is a particular type. And that then affects the way they're displayed in the packet tree. Integers are normally decimal, and timestamps are nicely formatted in time format. So declaring the appropriate types then makes your fields look good in the packet tree. And then dissectors also provide that those names of those elements, dissectors actually name each element that they pick apart, and that's used in the filter fields. So then when you have, in display filters, so when you have your dissector up and working, then the users can filter on specific fields and elements in your protocol. So what does a dissector actually output when it's run? It sets the protocol column, the name of the protocol, sets some information into the info column in the packet list. The info column is in effect a summary of what would be in that protocol packet. And you don't have to do that just once at the start. As you work through your packet, you may want to change what the info is because the later contents of the packet indicate something more specific. And you create tree entries as required, so that gets you in the packet tree the individual elements broken out into sub-elements depending on the complexity of your protocol. You create tree entries with sub-tree entries for these protocol components and keep eating through the bytes in the payload, adding to the entries as required. And then sometimes your protocol may be a transport protocol for something else. So you have to then call another sub-dissector. And if you've got one of these layered protocols, it's quite often more helpful when you're developing a dissector to actually do it as separate dissectors. Don't put it all in one big file. Separate these out as sub-dissectors. So, onto the meat of what we're going to look at today is some construction options for actually creating dissectors. And the first ones there are text-based. So all you need to do with these to build them is have a text editor. No programming really required, it's just text. It's text of a structured format though. And some of these are actually built into Wireshark itself. A lot of dissectors in Wireshark are from text specifications, ASN1 or IDL interface definition language. So these protocol specifications can be used by tools within Wireshark to create a dissector automatically. And a lot of dissectors in Wireshark are of that form. And there's also an external option that you don't have to compile called the Wireshark Generic Dissector, WSGD. And we'll come on to that. We'll look at the use of that in the next section. There's also scripting language-based dissectors. So if you're familiar with the scripting language, the built-in one we have is Lua. The ones I'm going to discuss today are the ones with the stars there. So Lua is a scripting language, quite popular for various tasks and techniques. And we have support within Wireshark for Lua-based dissectors. And there is at least one I know of, an external Python one called Wireshark. That's external to the project. We don't support that internally. To be honest, these days I don't know how far that's going. And then we have the last construction option, the traditional C-based dissectors. All the dissectors currently built into Wireshark are all C-based dissectors. I don't think we ship any Lua ones. Some of them are ASN or IDL derived, but the tools in Wireshark take those text protocol descriptions and then generates a C dissector file which is compiled. And of course some of the difficulty we go with a C-based dissector is that you've got to set up a development environment. You are actually programming here. On a Linux or Unix environment, not too bad because those are generally set up or easy to set up for a development environment. Windows is a bit more complicated. You've got to install a fair few packages and you've got to understand the Windows build system. Although we're currently moving the Windows build system over to CMake, so it will have the same equivalent. You can use CMake on Linux, which actually makes things a little bit easier. But still, setting up the Windows build environment is a bit of a task if you haven't done it before. The key to that build environment is there's a document on the Wireshark website, the Wireshark Developer's Guide. Absolutely gold. All the information in there is really essential if you're coming to set up a build environment and develop dissectors in Wireshark. It goes into a lot more than just dissectors, but the development guide really you must read and understand and get to grips with that because there's a gold mine of information in there. And the other source of information about dissectors and other things in Wireshark is in the doc directory of the sources. There's readme.dissectors, readme.design, readme.other things, and there's a lot of great information in there as well. So for the protocol this morning, I've just made up a little one. It's convenient for me because it's not in Wireshark, because if I use an existing protocol, Wireshark's already going to dissect that, so we need a brand new protocol that's never been seen before in Wireshark. So I've made up one that's similar to the sort of stuff that I see in my day job. It's a little protocol that has a header with a byte indicating the message type. Quite common in protocols, you've got some identifier what sort of message this is. And it has a length. Protocols that have length indicators are really good. Ones that don't are an absolute pain because you don't know how much data you're working with. And it's a protocol that has different commands. That's the message type. You have a connection to the remote end, an ACK coming back, and then you have, when you finish, a disconnect and a disconnect ACK. And then you actually want to get some data from the remote end, so you request data and get request reply. Usually, if you think about it, most protocols, all they're actually doing is transferring data from A to B, but we have to invent different ways of doing it every time. So that's why we have thousands of protocols. And I've mixed up the types of these datas to show little endian and big endian and different lengths of data. We've got the data that's been transferred is a short or a long or a character string. So we have this protocol, and now we're going to look at creating a dissector using the text-based WSGD. And the protocol definition for WSGD is just in a couple of text files. Human readable, you can edit them in Notepad if you wish, or any simple text editor. And these definitions then are interpreted by the WSGD DLL, I have to say, or library for Linux, and it's a very low barrier to entry because all you need is a text editor. The issue with it is it's pretty slow because the system is interpreting the text editor files every time. And it also gives you very limited access to the infrastructure in Wireshark for making your dissectors look good and do various complicated things in dissectors. So this, yeah, just going into WSGD now. It's actually external to the Wireshark project. It's created by Olivier Aveline in France. There's the URL there. And available for both Windows and Linux. But it's relatively simple to use. If your protocol's relatively simple, or if you're not a programmer, it may be a good place to start. It's a simple, I think it's on the next slide actually. To make WSGD work, you have, as I say, a DLL or a SO library on Linux, and you copy it into an appropriate place in your Wireshark installation, either the global plugins directory or the personal plugins directory. You can find out the location of those directories from the About menu, which and the tab on there in Wireshark show you where the directories are. And then you need to create the actual definition files for your protocol. And they can be in a number of places as specified by the list I have there. An environment variable, profiles directory, and various other directories. All the instructions for installing WSGD are on the website in the previous slide there. Not too difficult to do. And now we'll actually start to look at this protocol definition. I'm always a little wary of how these look to people because there's a bit of text to fit in and it doesn't sometimes show so well on the projectors. So at the top, starting from the top, obviously you want to identify the protocol so that users can see it in the packet tree and identify it. So you give it a long name and then a short name and an abbreviation. So I've been very creative here and called it the SharkFest'15 protocol. And then you need to, as I mentioned before, hook it into the Wireshark framework at the appropriate point. As I mentioned before, this protocol runs on TCP port 54321. So we use these command names on the left. These are WSGD command names, parent subfield, TCP port, parent subfield values, 54321. So that now says that this dissector is going to be called by TCP whenever they see traffic on 54321. And now we actually start indicating elements of our protocol. So we say we've got a message header type, and that's the keyword in WSGD, and we name the variable that we're going to identify that has that protocol type. And we also do the same with some ID field names and a title that will be shown in the info column, what the message size field, because WSGD likes to know the size, and then a function that's going to process the main body type. So we actually do two parts of processing, the header, and then depending on the function code, then we do the actual body message. And then we have this last field here that says we're actually going to do the final definitions of the protocol in a separate file, SF15fdesc. This is the way that WSGD structures it. You have the two files. I can't remember the name of this file at the moment, but it will come back to me in a couple of slides. And then you have the field descriptions in a second file, which you include with that statement at the bottom. So this is the first set of page of the field definitions. So we have an enumeration, and the key word there is enum8. That tells you that this is going to be a single byte field. And we have the values that those single byte fields are going to be using. So as I mentioned, my little protocol has a connect and a connect app and the request reply, and these are the integers chosen for it. And WSGD has a little shortcut. If your message is just, if the value is 1 on from the previous one, you just put a dash. You don't need to indicate all the values there. You could, if you wanted to be explicit. I'm just showing a feature there. And the hash bit on the right, I forgot to mention that, the hash is a comment. So from the hash onwards, those are all comment lines and they're ignored by WSGD. So that enumeration there is just indicating the message type field, and now we come on to the definition of the header, and they use the struct keyword and then the name of the field, and then you use some commands in the structure definition. Starts to look a little bit like programming now. It's if you've used C or something else, a structured language like that, you might start to recognise these things. It's obviously based on a programming language, but this is all these keywords are all particular to WSGD. So you set the byte order of the data, big endian, little endian. You indicate that we've got a function field which is of T-type message, which is that enumeration we've just done previously, so it's one of those values. We have a length field that's of uint16, so that's an unsigned integer of 16 bits or 2 bytes. And then we have the var string, which is going to be the info string. It has the hide keyword because we don't actually want this to go in the tree, it's going to go in the info field. And it uses the print keyword there, similar to a C printf function, and it says put the name of the function as a string. So that function field, as we said before, was a T-type message, which is one of these integers here, but instead of printing 20, 40 or 60 or 21, it actually prints out the string name, the name of it, connect-ack. So this now is converting integers into friendly usernames that your users can see when you're dissecting the protocol. So that part of the message header was big endian, and now we say we're switching back for little endian for the rest of it. It's a mixed up protocol. You wouldn't normally do these sort of things, messing around with the endian this, but I'm just trying to illustrate features. So now we have the second lot of field definitions where we're going through each of the message types. So a connect message has a header and then an ID. When we make a connection, we have a connection ID, and when we get an ACK connect back, the second message, the ID comes back. And you can see that's of type uint32. So this is a 4-byte unsigned integer through connection ID. And then we have the equivalent of the disconnect and disconnect ACK. And unsurprisingly, they're very similar with the same connection ID. And then the third lot of field definitions are actually looking at the data in the request data and request reply messages. We have another enumeration because within the request message you have to say what type of data you want to read, the short, the long, or the string, and again they have function code values. And then we have a request data message, which again has a header, same header we've been using all along, and it has the data ID field, one of those values up above. And then we have the request reply message, and this is probably the most interesting field in this protocol because it has a variant body on it depending on what type of data is being requested. So again, we have a header, we have the data ID telling us what type of data it's going to be, and then we use this switch statement here which switches on the data ID value. So depending on what the data ID value is, it will implement one of these three options below. So as we see there, data ID, up in the definition of the enumeration, a short is 0. So 0 does the first element in that switch block, and we're going to read the uint16, which is the size of a short. And then similarly, we read the long or we read the string. And again, we have to tell the types of the fields, or in the case of the string, how big the string is to read it. And there's a little bit of a safety net because some other engineer in your company might be making this protocol and changing things. We have an unknown message. If it's one of the message types that we haven't declared before, then we'll catch it in the unknown message, and you, at least in the protocol tree, you'll see it's an unknown message. Otherwise, your dissector may well cause an error in Wireshark that will say the dissector had aborted, hadn't finished reading the data or something else like that. So that's a little catch-all at the end. And the statement there, raw star, just says grab all the rest of the bytes in the message. Whatever's left, grab them and stick them in there. So that means that you clean up the rest of the protocol body data that was given to you for something you don't even know what it does. But at least you clear it out of the data, and it can be represented as a sequence of bytes in the packet tree. And this is the last bit of the field definitions. This is where we translate the integer numbers for the message types to the strings. And we have a default there for the message unknown. These are all, the keywords and all this is defined in the examples in WSGD. I just basically taken those examples and applied it to my little demonstration protocol. I have to admit, not as a Cdissector writer, I found it a little awkward and a little different, but if you were coming to it from the first point of view without knowledge of Cdissectors, I think it would be reasonably easy to follow. So what I'll do now is just give a little demonstration of what that, using those two files, looks like in Wireshark. Bear with me one moment. So this instance of Wireshark I have here has a WSGD DLL installed into it. So in plugins, there's the generic DLL there. And if I load the instance of my protocol, of course, now it doesn't fit on the monitor screen. So we have numerous number of packets there, just showing each of the message types, and we can see the protocol has put its abbreviation or its name, short name, in the protocol field, and then in the info field, it's showing the ports used to receive and request, and we have the names of the messages in the info field. And then looking at one of these in the packet tree, we can see the long name of the protocol, and it tells us the function that was used, the connect function. And then expanding this packet tree, as you would expect for any other protocol, we've got the header, we've broken it out into the function, it tells you the function value and the length value, and that the ID of this one is 0. And if we go to the most complicated one, which will be the request reply, expand fields, and we can see the request reply has been eaten here. It was a read string function, and it has the data string SharkFest'15. So two smallish text files, and now you've got dissection of a fairly simple protocol. And you can also use the filter fields. So SF15 there, all the fields we've named there. So if I do function equals 20, so that was the connect, the filter then just shows that connect message. So fairly simple text files allow you to dissect that protocol. Now, WSGD is somewhat limited in the features it can provide, but it is a fairly quick and simple method to get a basic protocol dissection. What I'll do now is close that. Next option then we have is scripting language-based dissectors. And now we're actually starting to get into programming, in my view. Again, the protocol definition that you're going to be using is held in a text file. This time you're constrained, again, by the keywords and things you use by the script language syntax itself. So if you're knowledgeable about Lua, then you'll recognize the language statements and so on. What you'll be doing in Lua, though, is calling into the Wireshark API using the Wireshark functions to dissect the protocol. And these definitions in the script file are loaded up by the scripting language runtime within Wireshark, and that runtime exposes all these live Wireshark infrastructure. Not all of the infrastructure is exposed. We are expanding Lua as more requests are made for more features, then they get expanded. So there will be some things you can't do in Lua that you can do in a C-based dissector, but it's getting few of those restrictions. Again, you don't need a development environment. You just need a text editor, although a text editor that maybe understands Lua syntax and color highlights or something like that would be useful. And the script language dissectors are faster than the text dissectors. Speed may not be an issue for you, but if you've got multi-gigabyte captures, then speed is very much of an issue for you. So the script languages, again, are rapid development, and they are faster to dissect data than text dissectors such as WSGD, but they are slower than a C dissector. So in Lua, we have Lua built in. It can be used to not only do dissectors, we've got post dissectors, which can run after another dissector to generate other info, and taps, which are used to generate statistics. In the Wireshark directory, config directory, we have an init.lua, and that controls the Lua runtime, and it has an option in it to disable Lua, but if that's not disabled, that gets run from the personal, also from the personal configuration directory. So you can actually use these init Lua files to load in your own dissector files or load in Lua libraries, other Lua libraries you might want to call, and then the Lua system will also run any scripts passed on the command line with the option -x Lua script, name of your Lua script. So there's a few ways to run Lua scripts. They're all on the Wireshark wiki for the Lua support. So now we're going to do a demonstration of Lua, and because Lua is a much more defined scripting language, I've been able to find a syntax highlighter and colorizer. So we've got various things coloured here. Very similar to start off to the WSGD, we declare our protocol names. I've differentiated it with Lua in the parenthesis at the end, just so we can see when we fire it up in Wireshark. So you create a protocol with the proto statement. Then we declare these message type value strings, VS_funcs I've called them. Again, you declare them as a Lua array with values, and then the string names. Same for the data type for the read and read reply message. And then you start to declare the fields that are going to be used in Lua. So you specify the you use the proto field command with the modifiers depending on the size of the field. So a uint8 for our functions, that's an 8-byte unsigned integer as we've seen before, and you give it the, in the quotes there, the filter name that will be used for the function, the long name, base dec, so that's telling you it's going to be a decimal number, and then you've got the VS_func string there, which indicates the mapping from the value, the integer, to the function name. Similarly, we've got the len is a uint16, which is the length of the message. we have the connection ID, UINT32, and so on with the data ID, and then the three data values used in a made-up protocol, the short, the long, and the string. Very similar to WSGD, you're basically saying these are my element types, and these are how big they are and what type they are. And you collect them all into a proto fields collection there, which will be used subsequently. So now we get into the meat of the dissector function. Now we've declared all these preliminaries. We are going to call this the SF'15 proto.dissector, and we get passed in some elements from the Wireshark framework. We get the buffer, which is the data that we're going to be using. That's the payload that we're going to be dissecting. P-info is a structure that contains lots of information that you're going to set or possibly use. And the tree is the current tree that Wireshark has already built, so that's Ethernet, IP, TCP, and you're going to be adding stuff to this tree. So first off, we set the protocol column. So in P-info, calls, subscripted by the protocol column, we're going to set the name of our protocol, SF'15 again. And then we're going to use the tree add function to create the top level protocol tree item for our protocol. And we set a local variable offset to 0. As we work through the buffer, we're going to increment offset as we eat the bytes out of the buffer. And now we quite linearly work through that buffer. So first of all, we've got a header, so we're going to add a tree item for the header. We've given it the string name of a header, and we've said it's going to run from offset, which is currently 0, for 3 bytes. That's the size of the header. And then we say that we're going to have the function code here is going to be in the buffer at offset 0 for 1 byte, and it's of type uint. And then in the tree we add the function code and we add the length, again using the offset values and the length of those fields. So we've finally managed to go through the header, so we increment offset to point past the header. Now it's pointing 3 bytes beyond, which is the size of our header. And now that we've read information from the header, we can now amend the info column to indicate which function type we're going to be using. Is this a connect, ACK, and so on. So we rewrite, write into the info field now the function code. And then some of the function codes have common fields in them, and the function code 20, 21, 60 or 61, so that's connect, ACK, disconnect and disconnect ACK, are all basically the same. They have a connection ID in them. So we have a bit of common code here. We add the field for the connection ID. And we use a type add underscore LE. This is a little endian field, which is where I'm messing around the endian, and it's currently an offset from 4 bytes on from offset. 4 bytes length starting from offset. So that there, little block there, is a common part that's just used for the those 4 functions. And then the more complex function is the request data or request reply message. So that's the 40 or 41. They both have a common part. They both have a data ID integer field, so we add that. And then we work through, on the particular message for request reply, we work through the various types of data that can be in the reply. Very similar again, we're going to say this is either use the data ID value to indicate which type it is. So if it's 0, we're going to read the short, little endian short of 2 bytes. If the data ID is 1, then we're going to add the long item and add LE again, but this time it's long, it's 4 bytes for a long. Or we're going to read the string, so it's going to be 15 bytes of a string. And then the final part of the dissector is dissector registration, which we did at the front of WSGD. In Lua, we usually do it at the end. We're going to grab the TCP table, which is the table of all dissectors registered with the TCP dissector, and then we're going to add an entry to it at port 54321 for our protocol that we've defined in the earlier fields. So now we get to see the demonstration of the Lua version. So again, very similar to the display before, we have the protocol field has been set and the info field. No, slightly different display for reasons unknown to me. WSGD would like to put square brackets around them, but the Lua one, we just have the straight strings, and then pretty much the same representation in the tree. Name of the protocol, the header field, and then if I go to the request reply, we can see again pretty much the same as we had before, because using the same infrastructure and defining the protocol the same. So with Lua, you're now moving into the realms of much more a programming language, but it's still a very lightweight development environment. It's just a text editor, and if you have Lua knowledge, then you'll be up and running with it pretty quickly. But the Lua dissectors they are allowed to use a lot more of the Wireshark infrastructure, and as I mentioned, they can be run as also post dissectors or taps to generate statistics, which you may need. Lua dissectors can also add entries to the menu. You can add entries to the statistics menu for particular statistics for your protocol. So a lot more flexible with Lua, but it is a fair bit more complex up from WSDG. So next, the traditional C-based dissectors. So this is using standard C. You create a source file or more than one source file, and that will have the protocol definition in the functions that you define in the source file. And the dissector source file will either be compiled into Live Wireshark. You can build your own copy of Live Wireshark. Just, I forgot to mention earlier, what you have the Wireshark executable, wireshark.exe or equivalent on Linux. And then Live Wireshark is a DLL or a SO dynamic library loaded into the application, which contains all the dissectors. So Live Wireshark is the big lump that contains all the dissectors. Or you can generate your C-based dissector as a plugin in the plugins directory. So that means you could create a plugin and then distribute that plugin to everybody. You don't have to distribute the whole Wireshark installer. I might mention here, just as a slight side issue, when you use Lua or C, you are subject to the GPL. Wireshark is released under the GPL, and using Lua or C, you are linking with the binary, so you're subject to the GPL requirements, which means you can freely distribute as long as you give the source to those who request it. You can distribute within a company without having to release the source. Once it goes outside your company to customers or something else, you're legally obliged to make the source available. So there are a number of companies around who have their plugins as proprietary plugins, but they only use them within the company. And that's fine, but just a little note there. So within the C-based dissector, fairly obviously, you've got access to all the Live Wireshark infrastructure. Live Wireshark is built around C-based dissectors. You have everything there. But you do need that full development environment. You need to be able to set up, you need your compilers, you need linkers and everything else required to create the C-based dissectors. And there is a fairly high knowledge barrier. There's a fair bit you've got to get through to actually create a C-based dissector. But you have a huge amount of existing dissectors you can look at. Some of them are easier, some of them are more complex. If you know an existing protocol well, then you can look at the dissector of that protocol, if it's supporting Wireshark, as a guide to where you need to be going. And as I've mentioned earlier, the developer's guide is essential reading if you're going to embark on this, along with readme.developer. So, when you're going to be developing a C-based dissector, the installation of the source files, normally for a built-in dissector, we go in the EPAN dissectors directory. They're all named packet-protocol names, so you have packet.tcp or -tcp and so on. And then you have to add that dissector source file to the lists of source files to be compiled. We have, unfortunately, several ways of building, so you have to add it to multiple lists, makefile.common or the cmake list.txt. Again, the developer's guide will tell you where to go on that. And then you can, when you're testing, developing, you can quickly compile your packet, just to your source file, just to test that you've got your syntax straight. Usually, as in C, normal C programming, very strict on syntax. And then you build Wireshark in the normal way, as in the developer's guide, and your dissector will be built into the Wireshark library and come up within Wireshark. Now this is where it gets to be really complicated, because I need to get a lot of text in. I've actually got, if it works, there we go, we can just zoom in a little bit, hopefully it's a little bit bigger, although the text starts to go very jaggy. First of all, as a typical in a C program, you've got to pull in definitions from somewhere else. So we've got some includes at the top. Config.h is the main Wireshark configuration file, tells you all sorts of things. glib.h, we use a lot of functions from glib, which is a generic C library that gives us a lot of useful functions. And as you're building a dissector, you need packet.h from EPAN. There's a lot of functions there. And then, similarly as we've seen in the other ways of building a dissector, you start to define some unique values in your protocol. So we've got the port and then those message type functions that we've seen previously. We've got then a definition of the minimum length of our protocol. In a C-based dissector, you really should check how many bytes you've been given, and if you haven't got enough, you can't dissect it, so you tell the framework, not for me. So we've got a minimum length of 4. We've got then what's called a value string array in C, which is where we connect the values that we've defined up before for the message types, 20, 21, with the actual strings that represent those message types. Very common in C-based dissectors, every one of those will have this sort of field, and you end it with a 0 null to indicate that's the last message. Then we're defining some more values. These are the data type values, the short, long, and string, and again define the definitions of those in string terms in a value string array. Then we come on to some more values that you need to declare in a C-based dissector. These are values, the HF underscore are the header fields. These are the actual fields in your protocol. And you also need the proto-SF'15. That's going to be your handle to your protocol, which will be used when you register with TCP. So you've got to have a lot of setup of fields and so on, pre-declarations. We all initialize them to -1, and they then get initialized when the dissectors run. And then for subtrees, these are the header subtree and the data subtree that you saw in the tree representation. We need these variables, again, traditionally called ETT fields within C-based dissectors. I'll expand this one again. So now we're actually going to declare our dissection function, dissect SF'15. And now, of course, you see in a C-based dissector, you get past lots more information. You get past the infamous TVB, TV buff underscore T. It's a testable virtual buffer. It's a specific data type in Wireshark that allows dissectors to probe into memory, and if they make a mistake and go off the end of the memory block, bad things don't happen. It's a typical C program issue, buffer overflows. Notorious for security issues, so we've tried to provide a safe buffer that dissectors can poke around in, and if they go off the end of it, we catch that and they won't break the application. So that's a sort of security benefit, but it means that you have to know how to handle TVBs, and there's a lot of information in the docs about those. You get handed the packet info, the P info field, very similar to Lua, and the proto tree, the star tree field. And then dissectors can also be passed a data field that can hold other information, and the underscore U underscore indicates that this is actually unused in this protocol. When you compile these, and if you don't indicate fields are unused, then your compiler will generate warnings, so it's just a warning suppression. And we declare variables at the front of it that we're going to have some proto items, that's the actual protocol tree and the header tree, header items, sorry, and then the trees that we're going to be using, the protocol tree and the header tree, and then some other variables that we use. Typically, again, we use offset as we work our way through the buffer. The offset indicates where we are in the buffer. The function code field is going to be the function code we read from the message, and the data ID is the data type field. So then, typical of a C-based dissector, we test the length of the buffer passed in, the TVB. We ask the TVB length. If it's less than our minimum length, 4 bytes, well, we know it's not for us, it's not big enough. So we return immediately, and we return 0, saying we did not dissect this. That would mean that it might be some other traffic on port 54321 from something else. And we've decided it's not for us, we'll hand it back. A heuristic dissector might pick it up, or another dissector. You can also do more complicated checks there, which we're now coming on to in the second section. We know our protocol really should have one of those 6 value types. It should be a connect ACK, disconnect ACK, read or reply data. So what we do now is actually check, is the function code one of those we expect? So in the C-based dissector, if it's not one of our function codes, we're out of there. It's not a message for us. We allow somebody else to dissect it. And now we start to set the columns. We think this data is for us. It's one of our function codes, and it's of the minimum length we need. So we call, now this is where we start getting into the huge Wireshark API. We start to call column functions to set the values. So col setstra sets the protocol column to the name of our protocol, SF15. We clear the info column because a previous dissector in the stack, the TCP, will have put info in the info column, and that would carry forward unless we overwrite it. So we clear the info column, and then we add the string that we're going to use on our protocol. And we use the val to str function there to convert the number into the string name. And we have a default value there. Although due to the previous code we won't get a value we don't know, but it's just a safety. If it was a function code we didn't know about, then we print unknown function and the actual function code number. So now we're actually going to start to display the protocol trees. So we use proto tree add item. These, again, this is where you need to look at readme.dissector. It lists all these functions, there's lots of them. So we're going to add an item to the tree, and it's for the proto SF15. We're going to use the TVB we've been passed in. It's an offset 0, and -1 means the whole of the rest of the TVB. And the last string there, enc NA, means we're not indicating any encoding to this protocol. You can have little endian, big endian, and so on. And then given that tree that we created with proto-tree add item, the TI field, we're going to add a subtree to it for our protocol. So then we call in the extra functions. And now we want the extra subtree for the header, so we do proto-tree add text onto the tree we previously got from the TVB, starting at offset 0, and it's 3 bytes long. Our header is 3 bytes long, and give it the name header. And then we actually create a tree from that text that we've added to the existing protocol tree. We create a subtree for the header. And now we get on to the meat of the dissector. I've commented there where in the README developer you see more information about that. We call proto-tree add item. So now we're going to add a particular item to the tree that the next tree there, the SF'15 header tree. We're going to pass in the header field, the function code field, pass in the TVB that we're using, our current offset, it's 1 byte and it's little endian. So now we've consumed that byte in the buffer, we bump offset on by 1 byte, and we continue adding on protocol items. So we have, again, proto add item now for the length, encoding big endian for the length, bump the offset on, and now we use a switch statement on the function code. So the 4 common types, connect, connect, ACK, disconnect, disconnect, ACK. We're going to add the item for the connect ID, 4 bytes, little endian, bump the offset on, break. Are we okay with that? Do we need to zoom that, or are we okay? So now we're doing the request data. If sorry, my formatting's gone a little odd there. If it was a request data or a request reply, we've got a bit of common function. Again, the data ID is common to both those request codes, so we add that to the tree. And if it's a reply, we need to switch on the data ID depending on which value it is to read the short or a long or a string. And again, we call proto-tree add item. Generally, you call proto-tree add item all the time. Proto-tree add item, proto-tree add item all the time, passing in the different HF field, the header field value that indicates how that data type, how that item, what its type is, and how it's to be represented in the system. So we've eaten the rest of the data there, and then so offset now points to the off the end of the data which we've consumed, and we return that. So that actually allows TCP or other dissectors, say we had within a TCP stream, how you would achieve that, I don't know in TCP, but we would have our protocol and something else, then we return that something else that could be consumed by another dissector. Now, I do need to zoom this one. So now this is another very common aspect of C dissectors. We indicate these HF fields, the header fields. And this is where we actually define these elements, give them a name, the function here, for instance the top one, the function code, we give it its long name function, we give it its display filter name, sf15.func. We declare the type, field type uint8, so this is an unsigned integer of 8 bits. It's decimal we're going to display. We have a conversion function, the vowels function, which will convert the function code to the function name. I can't remember what the OX0 is, I think it's a bit mask. You can isolate individual bits in a value. We have the really long name for the message that's shown in the status bar at the bottom, and then the H field, whether the fields, I think that's to be initialized to 0 or not. I forget, but you always put H field on the end. So we do that for each of the fields in our protocol. We have the name of the field and the types and the representations. So pretty much a C-based dissector has reams of these for all the different fields. So this is part of the protocol registration with the Wireshark framework. And then the second part, Sorry for all the jumping displays. We set up an array of the ETT fields, these are the subtrees, and now we register our protocol with the framework, the proto register protocol command. I've missed one bit from last year, that should be SharkFest'15, where I rubbed the 14 off and put 15 on. And then we have to register our field array, which was all those HF fields that we had before, and we have to register our subtree array. So that function there registers everything to do with our dissector with the Wireshark framework. And the last field that we have is proto-reg handoff, SharkFest'15. This is now where we actually hook it finally up to the TCP dissector on our particular port. We have to create a dissector handle for it, so a new create dissector handle, passing in the function that's going to be used to dissect it, and then we add that dissector to the TCP port table on our port using the handle we created earlier. So these are little bits of boilerplate stuff that in a C-based dissector you've got to do all these common things. Every C-based dissector has this, and you'll see it throughout the code base. These are the boilerplate functions you need to do to register with the system. Having done all that, we'll just do the quick demo of somewhere, it'll be in here. C-based dissector, and unsurprisingly it looks pretty much the same as the other ones. So again, we see we've got the protocol field, the connect, the message type in the info field, and then select request reply. Slightly different formatting, I think. Oh no, I didn't expand header. There we go. So very similar to what we've seen in the others. So all three effectively produce the same sort of display. It's just the level of effort required to achieve that. So yes, for that simple protocol, almost identical. WSGD and Lua are fairly quick to develop. You just edit the file and restart Wireshark. The facilities in WSGD are limited. Lua a lot more advanced. Cdissectors are fairly easy to distribute because you can build a Wireshark installer package, or just build a package with if you do it as a plugin, you can distribute it as a plugin. And also much easier to contribute back to Wireshark. We've given you all these dissectors for free. We'd much like you to give all your dissectors to us as well. We will maintain them for you then. Obviously, in the case of proprietary protocols, that's not going to happen. But if you do develop something useful, by all means contribute it back, and then we'll maintain it for free for you. Just as a comparison between the three there, WSGD was 124 lines, Lua is 89 lines, and C was 270 lines. So that's a little bit of a comparison of the effort of the required. And then I did a quick check on this laptop of the dissector performance. For that little capture I demonstrated there, you don't notice the difference. Then I tried a bigger version with 1 megapackets, and we can see the comparison times there. WSGD 9 times slower than C, and Lua 2.4 times slower than C. So again, that may not be an issue to you if you're just doing small captures and the speed of deployment with, say, Lua or something is, you're happy with Lua, then that's fine. But if you're looking for ultimate performance on large captures, then you've really got to go to a C-based dissector. Sorry?
You were JIT.
I think somebody's looking at that, but I'm not a Lua guy, so I can't really say. That's about it. So yes, questions, feel free to ask. You were going to say that?
I was just going to ask, it looks like the custom dissectors are called before the TCP dissector. Is that a correct statement?
No. Basically, the way the Wireshark framework works is that the capture is either loaded or a live capture. You'll have a linked layer type that indicates where you're capturing from, Ethernet or 802.11. So then there's a dissector for the linked layer type. So Ethernet will get called. And then you get the protocol in field in Ethernet that tells you it's IP. And then you get in IP, it tells you TCP. And then for TCP has a big table of all the registered dissectors for TCP on particular ports. So it's on port 54321 and we're registered there. It varies for different protocols, but it's basically run that way from the link layer type through to working up the stack, if you think of it that way.
This example protocol that you created, it's a protocol that runs on top of TCP, but we didn't see the TCP layer dissected, or displayed, right? It went right to your...
No, it should have been in there.
Oh, is it?
Bear with me. I just skipped over that bit because I didn't think it was interesting. So there we've got the standard stack, Ethernet, IP, TCP, and then our protocol. Yes?
So, so you registered a thing. Is there? How does Wireshark handle, or does it handle an issue where you've got more than one, either just a port number that someone else is using, either something that's built in and you want to override, or
decode as.
Decode as. Okay. Well, so do you have to worry about that while you're writing it, or do you just?
No. I mean, obviously, if you've got a specific assigned port, then you.
Sure. But I mean, so like if you expect, okay, well, this is all going to go on 80, but I want this to be handled differently than HTTP.
Yeah.
Or I want this. I suppose we could hook into HTTP the same way that you hooked into TCP as well.
HTTP has a sub-dissector for like MIME media types or things like that. So if you're using that as your bearer protocol, as it were, then you hook in those ways. The obvious awkward one is if your protocol is run on a well-known port, for instance, for something else, like you really want to use port 80 for something else, then you are going to have to disable the HTTP dissector.
Okay.
I'm not. You might be able to do that programmatically. I don't think so. You might just have to disable that protocol.
Does it? It doesn't cause any problems. It's just it's going to prefer the built-in ones to the stuff that
there is an order. I think it's the registration order of dissectors. Okay. Last in wins may well be the case.
Okay.
You mentioned the decode as option. If you create a dissector with WSGD or Lua, does it show up in that?
Yes.
As an option?
Yes. Yeah. Decode as will handle all registered dissectors. I mean, you can register. If you register with TCP port 0, you're saying I have no specific preference, and you're actually basically becoming a heuristic dissector there. You'll get handed data that's not handed to a registered port dissector, and you've got to determine, is this for me or not?
In case if, let's say, protocol is delivered like motion like yields, you write two dissectors?
No, you write one dissector and you register it twice, or you usually have a little header function, dissect TCP, dissect UDP, and you register both those, but they default then to your main dissector body. Sorry?
It's the same, it's no changes.
Yeah. Well, I mean, the slight difference is because TCP, because it's stream-based, you might want to reassemble over multiple TCP packets. I just choose TCP because it's easier for me. But yeah, you can register with UDP or various others. There's many places you can hook your dissector in as required as to where it is in the stack. So the other dissector I work on, DMP3, that does both UDP and TCP. But it has to do reassembly because packets can be spread over, protocol packets can be spread over multiple TCP packets or UDP packets. And the disassembly is slightly different in both cases. TCP, there's inbuilt support for reassembling, because it's in a stream. It's much easier to reassemble packets in the stream. I didn't show those advanced reassembly, quite important in certain protocols, and it's a function that's available, but that's an advanced function, I would say.
In the output, we didn't see the TCP connection set up as SYNAC ACK.
It's there.
Went to your.
I filtered it when I did the captures, I think. I filtered it when I made those captures. I was just trying to demonstrate the protocol.
And then the final frame we did see.
Yeah, I had one prep through.
So your dissector gets fired up when you see the port 54321. Is there a way to have multiple criteria?
Yes, you can register for multiple ports, port range. But I say if your protocol is dynamic, it's not just one fixed port, then you're better off using a heuristic dissector and examining the header bytes and seeing if it's for you or not.
Can you build an application-specific dissector? If you're using HTTP for an API call and you wanted to just decode the API calls to your specific application?
So it'd be something like SOAP or something.
Yeah.
Well, there is SOAP stuff in there. I think we can actually use SOAP. Might be able to use like the WSDL or something like that. It's not something I particularly looked at, but you might be able to use your SOAP definition of your service and actually automatically create a dissector from that, similar to ASN1 and IDL. But you can hook in, there's various hooks into HTTP. Again, not an area I use much. Looking at things like media types, my media types.
Yeah, you mentioned sub-dissector, so I just wondered how you would use a sub-dissector inside the another layer.
Well, you've got two options. If you're hooking into an existing table in that dissector, so if HTTP has a table for, say, my media types, you just add yourself to the table and you'll be called as appropriate. If, however, you're more intricately linked in, shall we say, into the protocol, that you would need special handling to call the sub-dissector, then you are going to have to change code in the dissector below you, as it were, in stack, to make it call.
In the protocol that you created for this example,
yeah,
that was like a connection setup, connection acknowledgement, request,
yeah,
reply. Is there, that would imply that the client and server are using some kind of state machine.
Yeah.
So is there a way, since we're only looking at kind of like at one frame at a time,
yeah,
is there a recommended way that you would, will we add maybe another tree value to say, hey, this is a
That's a topic called conversations. Within the live Wireshark, we have conversation tracking. So in your dissector, you can say this is the first frame in a conversation. In our case, we'd look at the connect ID or something like that. And then you would then say subsequent packets all belong to that conversation. And then Wireshark will add extra fields to your protocol saying this is a reply to the frame in X. So that you get that with conversation tracking. Again, that's an advanced part of dissector writing.
Is that how you would also flag things? So you're structured as a reply, but
yeah,
I didn't see.
Yeah, that's where you can do expert infos or something like that. You can say the conversation doesn't look right here. There's something odd about this, and you would call an expert info function to flag that up.
Is that stuff available in Lua?
Expert info, yeah, and conversation tracking. Yeah. Obviously, your protocol. This is where you sometimes end up with a fight with the protocol, that there's not sufficient information in the protocol to track connections. Hopefully you've got an ID field in each message that allows you to track them along. Okay, I think we're all done. Thank you very much for coming. Hope you weren't too bored.